Okay. Yeah. Okay. Thank you. So we will start the online lab now. So for the laboratory one of the fluid mechanics, so it's related to internal flow and it's about the pipe flow experiment. For the material of the lab report one, you can see it in the lab material section. For the laboratory one, you will see the pipe flow experiment and the data of the pipe flow that you need to do for your calculation for the lab report. And you also can see the video and the recording of the pipe flow experiment. And you also can see the pipe flow marking criteria. And another one, the video that teach you know how to use the multi diagram. You need to use multi diagram to get the friction coefficient to do the calculation. Or you also can find it in module 5 section for the lab report 1. You can see the video and the data with the note. It will be the same for this one. Pipe friction notes, this one related to the calculation for part A. For the lab report 1, we have two parts, part A and part B. All the formula that you need, they give you in this file. And this one, sample calculation for the venturi orifice and sudden expansion, is for the calculation part B. The lab note, everything that you need is in lab note. Is about the structure, how to write the lab report. And as I said before, we have two parts. Part A, friction loss in pipe flow, and part B, measurement of flow rate in pipe flow. So the aim of this experiment, run real experiment with the instrument and measurement relating to the fluid flow. Highlight some key aspects of flow in pipe, friction loss, and verify theory. Provide the opportunity for working collaboratively and writing technical report. So you need to understand the Bernoulli equation and continuity equation or the mass conservation. This one you need to use for the calculation. Bernoulli equation and mass conservation you will study in week 6, I think. And for the Bernoulli equation, it is the energy equation, but the energy equation in this case is for the ideal flow. Bernoulli equation, we have three terms of the energy: pressure energy, kinetic energy, and potential energy. Pressure energy, pressure divided by rho g, and kinetic energy, v square over 2g. V is the velocity. Potential energy is the z, that is the elevation. So we need to use Bernoulli equation between 2 points to do the calculation. E in equal to E out, energy in equal to energy out. This one is 0.1 and this one is 0.2. So it will be P1 over rho g. This is for the pressure energy plus V1 square over 2g is the kinetic energy plus Z1 is the elevation, equal to 0.2. P2 over rho g plus V2 square over 2g plus Z2. And we also have HL, energy loss. For the energy loss, is it a combination between major loss and minor loss? For the major loss, we can say this one is friction loss or head loss, HF. You need to find HF for part B. Oh, sorry, part A. F, friction factor, multiplied by LD. L is the pipe length, D is the pipe diameter. You should use inside diameter. Multiplied by V square over 2G. V is the velocity and G is the gravity. And for the minor loss, HL, minor equal to the summation of KL is the loss coefficient multiplied by V square over 2G. V is the velocity. And for the mass conservation or continuity equation, we have here is the object like this, and we have the control volume, the red line. This is the control volume. We will have mass in and mass out. For the mass conservation or continuity equation, the summation of M in equal to the summation of M out. So you need to apply Bernoulli equation and mass conservation for your calculation. So for the major loss and minor loss, the energy required to push the water through a pipe is dissipated as friction pressure loss. For the major loss, it will occur due to friction within a pipe, and the minor loss occur at a chain of section, valve, bend, or other interruption. So we will start with part A. Friction loss in pipe flow. So this figure is the whole pipe flow ridge. We have the water tank here. When we turn on the pump here, the water in the tank will go to the pump, and then from the pump, the water will go to the flow meter. For the flow meter, you will get the flow rate from here. And then it will go to the pipe. Here is the pipe. We have 5 pipes. This is the pipe inlet here. And here is the pipe outlet. And then the water will go back to the tank again. And we also have digital manometer. Digital manometer will collect the pressure tapping between 2 points, between here, this point, and between this point. So for this one, you will get delta P, pressure drop. From here. And for the instrument, no, I didn't record. We already upload the recording for the experiment in UTS Canvas. You can have a look there. No, I didn't record it. So for the instrument, we have 5 pipes. Pipe 1 to 5, pipe 1 to pipe 4. Oh, actually, I made this slide by myself. If you need this one, I can give it to you later. You can give me an email if you want. So pipe 1 and pipe 4 is for the experiment part A, friction loss in pipe flow. Here, pipe 1, 2, 3, and 4. For pipe 1, is it the small PVC pipe? Pipe 2, small galvanized pipe. Pipe 3 is the big PVC pipe. Pipe 4 is the big galvanized pipe. And for pipe 5, is it for the experiment part B. So here is the data for part A. The pipe material, PVC and galvanized. The pipe diameter, PVC 1, PVC for pipe 1 and galvanized for pipe 2, PVC for pipe 3 and galvanized for pipe 4. So we provide the data for you only this one, the big PVC and the big galvanized. And internal diameter will be 28.1 millimeter, outside 33.7 millimeter. This one is for PVC. For the galvanized, the internal diameter 27.3 millimeter and the outside diameter is 33.7. So to do the calculation for part A, you need to use internal diameter, only internal diameter, and the pipe length between pressure measuring point, L, is will be equal to 2,550 millimeter. So when you do the calculation, I think you need to convert it into SI unit, that is meter. And the ambient temperature, you can use 70 degrees directly. Water viscosity, 1.002 times 10 negative 3 kilogram per meter second. This one you can find it from table A3 based on the water temperature, that is 20 degrees Celsius. So each group of students would do 2 flow rates on one PVC and one galvanized pipe. So it means that you have to select 2 sets for the PVC and 2 sets for the galvanized. And the difference of the flow rate should not be less than 30%. So for example, I select 58 and 46. The difference is 26%, and it is less than 30%. So we can't use this one, cannot. And don't forget that you need to include your calculation. At least one set of data for each part A and part B. So next I will tell you about the process of the experiment. The first step, turn on the pump and wait until steady flow has been established. In this case, I think we can wait around 30 seconds to get steady. And then you will get the ambient temperature. And after that, you will be able to get corresponding water viscosity based on the water temperature. Then you can get the surface roughness here. And note that the surface roughness for the PVC or the plastic is the 0. So after that, you need to determine the relative roughness. The relative roughness equal to the roughness divided by the diameter, the pipe diameter, and should be inside diameter. And then you will take the pressure drop reading from pressure differential on digital manometer in Pascal. And this one we call the delta P measure. You can get it from data sheet as I showed you before. And then step 3, you read the flow rate. You read the water flow rate on the flow meter Q. And again, you get it from data sheet. So actually, if we can go to the campus, you will have to do these 3 steps, but now we can't. We have to run it online. And next, you need to calculate the flow velocity in a pipe. Velocity will be equal to the flow rate divided by the area. The flow rate, you get it from step 3. And for the area, cross-sectional area of the pipe pi d square over 4. D is the inside diameter. And then you need to determine the Reynolds number. Again, Reynolds number will be equal to density rho multiplied by velocity and multiplied by the inside diameter and divided by the dynamic viscosity. So from the Reynolds number and the relative roughness, you will be able to find the friction coefficient F from Moody diagram. You can see the Moody diagram in the appendix, figure A12. Here is the Moody diagram. So this one is for the Reynolds number, and this one is for relative roughness. This one is friction coefficient that we need to find out. And as I said before, you need to find the roughness. The roughness of the PVC is made from the plastic here. Small section here. You will have the roughness in this case is 0 millimeter. And for the galvanized iron here, you will have the roughness 0.15 millimeter. So for example, if we get the Reynolds number around here, and we get the relative roughness around here, this is the intersection point, and you have to draw it in horizontal line. Here, you will get the friction factor or friction coefficient from here. You can see the video how to find the friction coefficient, how to use Moody diagram on UTS canvas. So after that, you will be able to find the friction head loss or friction loss HF. We already get the friction factor from the previous one, and again L multiplied by L over D. L is a pipe length 2550 millimeter. Again, you need to convert it into SI unit, that is meter. D is the pipe diameter, inside pipe diameter. V is the fluid velocity, and divide by 2G. G is the gravity, is constant, that is 9.81 meter per second square. Then step 7, you need to calculate friction pressure drop, or we call delta P calculated. It will be equal to density, gravity, and friction head loss that we get from this step. After that, step 8, you need to compare delta P calculated from step 7 with delta P measure from the measurement from step 2. And then you need to make the comment on the agreement or lack of it. Offer the explanation discussed as per suggestion on the reference note, pipe flow experiment. So don't forget about this. You need to include your calculation in your lab report. This one is very important. Do you have any question for part A? Here is part B. Actually, you can have a look in UTS Canvas. They already upload everything that you need for your lab report there. So I will start with part B, the measurement of the flow rate in pipe flow. So remember this. The sample calculation for part B is already provided on the UTS Canvas site. You can have a look there. You can get more detail. So again, as I said before, we will wait on part B and pipe 5 here. For the instrument, we have 3 things. The first one is the venturi, second one is the orifice, and another one is sudden expansion. For the data, divide ventrimeter, orifice plate, and sudden enlargement fitting. Again, ambient temperature is 20 degrees Celsius and water density is 1,000 kg per meter cube. You can find it appendix table A3. And again, each group of students would do 2 flow rate on venturi, orifice, or an sudden expansion. So, the process of the experiment, part B. Again, we start with turn on the pump and wait until steady flow has been established. And then you need to read the flow rate, the water flow rate. On the flow meter, we call the Q measure. You get it from the data sheet again. Then you need to read off from the digital manometer for the pressure change for the venturi, orifice, and sudden expansion. And again, you need to select two sets for venturi, two sets for orifice, and two sets for sudden expansion. So for example, if I select 42 and 26, the difference will be 61%, more than 30%. So we can use this one. And again, the calculation for at least one set of data for each part A and part B. So now I will tell you about the process of the experiment. This is step 4. From the pressure change, we need to calculate the flow rate through the venturi and the orifice. You can see the note with page BPH for the calculation method and the formula. So in this case, we have to use Q measure to find out the Reynolds number first. For the Reynolds number, this one is different from another one that I told you. 4 multiplied by the density and multiplied by the Q measure divided by pi d and mu. And then when you get the Reynolds number, you will be able to find out CV, venturimeter coefficient, and C, the orifice meter coefficient from the graph on the left note. Here is the graph. For the CV, venturimeter coefficient, here is the Reynolds number. We need to base on the Reynolds number and here, capital D multiplied by D. So I will tell you later what is this one. And then you will be able to get CV, venturimeter coefficient. So for the orifice meter coefficient C, you also need to find out the Reynolds number and D divided by capital D. So we still in the step 4, calculate the flow rate, but this one for the venturi. From this formula is come from Bernoulli equation. And for the Bernoulli equation, we don't need Z1 and Z2 because it's same elevation. So we can cancel out this one. So here is the final term for the flow rate for venturi. CV, venturimeter coefficient, we get it from the graph. A1 and A2, area at section 1 and 2. Here is the A2 is come from the small section, this area, from D. And A1 is from capital D or the last section here. Delta P is it a pressure change? You already get it from the data sheet. G, gravity. And as I said before, Z1 and Z2 elevation, we don't need it because it is the same elevation. To find the area again, we can apply this one. pi d square over 4. So this one is the flow rate for orifice. Again, Bernoulli equation. And we don't need Z1 and Z2 because it's the same elevation. And C is the orifice meter coefficient. When we simplify it, we will get the flow rate for orifice. This one. C again. Orifice meter coefficient. A is area. Orifice area. And delta P again, pressure change. We already get it from data sheet. And G gravity 9.81. In this case, we consider only here pi d square over 4. Only small section, small diameter. This one is for orifice. And then when you get the flow rate for venturi and the orifice, you need to compare it with the flow rate from the measurement. And then you need to make the comment on the comparison, accuracy, uncertainty, or etc. This one is for venturi and orifice. Do you have any question about this? So the flow rate for the sudden expansion from the pressure change that you get it from data sheet and refer to the textbook for the loss coefficient KL for the sudden expansion. You need to calculate the flow velocity V1. Again, we need to apply the Bernoulli equation here, and we can cancel out Z1 and Z2, same elevation. Then simplify it, we will get this term, final term. So we need to find V1. In order to find V1, delta P we already know, density, gravity, we already know about this. We don't know V2 and we don't know HL. It means that we need to find V2 and we need to find HL. We need to apply another equation, continuity equation or mass conservation. For the mass conservation, again, M in equal to M out. So volume flow rate Q equal to velocity multiplied by cross-sectional area. So based on the mass conservation, M in equal to M out, Q1 will be equal to Q2, or V1 multiplied by A1 will be equal to V2 multiplied by A2. Simplify it, we will get V2 here equal to V1 multiplied by A1 divided by A2. So we know V2 from this one. And we also need to find out HL, energy loss. We can find it from minor loss equal to KL, loss coefficient, multiplied by V1 square over 2G. So we just substitute it, and then we will be able to find the flow velocity V1. And then after that, this is our target. We need to calculate flow rate. Q calculated equal to V1 that we got from here multiplied by A1. So here is D1, here is D2. D1 is the small area, small diameter, sorry, and D2 is the large diameter, is around here. And in order to get KL, the loss coefficient, we need to find A1 divided by A2. A1 is here, small diameter, and A2 is the large diameter. So then Step 8, you need to compare the flow rate that you got from the calculation and with the flow rate that you got from the measurement. And then you need to make the comment on the comparison again, accuracy, uncertainty. And remember this one, simple calculation for part B is already provided on this Canvas site. You can have a look there. It will be more detailed. So don't forget about this. Include your calculation in your lab report. So about the report, you should include the title, name of the report author. The abstract, you can write it around 1 or 2 sentences. The introduction, methodology, results, discussion, conclusion, and acknowledgement. You can include the reference and the appendix. So you can see more detail in BPH lab note. For the marking criteria, we have four main parts. The first one, on-time submission with the quality, 25%. Quality of lab report, 25%, and the completeness of interpretation and discussion, 25%, and correctness of application of theory is 25%. So again, on-time submission, you will get maximum mark, 25%, and the quality of lab report refer to above report in the lab note. Again, showing calculation. You will get the maximum mark is 25%. And another 25% it comes from interpretation and discussion. Another 25 will be the application of theory and the result from part A, 13%, and part B, 12%. So the item for discussion, you should include the usefulness of the experiment and the accuracy of measure value, arrangement between theory and the experiment, author experiment with the present setup and its extension, the way to improve the experiment and learning process. Do you have any question about part B? Okay. Actually, that's it for online lab 1. So you can see the material on UTS Canvas site. So I can show you something about this. Sorry, not this one. Can you see my screen about the pipe flow experiment? Oh, yes. So you can see here is the sample calculation for the venturi meter and olefin rate. So you can see this part. You compare the calculation for the flow rate with the flow rate from the measurement, and for this one, it is very good agreement if the difference between the flow rate calculation and the flow rate for the measurement is less than 5%. It is very good agreement, and if it is less than 10%, it is that we accept that. So you can say this one. for the flow rate calculation is 7.9 and for the measurement is 36. This one is slightly different. So you can compare like this. For the sudden expansion here, only fair agreement because this one is for calculation is 50.9 and measurement is 42. Yes, actually, if the difference is more than 10%, we not accept that. But you just write it down. Yes, I will show you the data. Here is the data for part A, friction loss in pipe flow. And here in part B, measurement of flow in the pipe. You need to select two sets of each venturi orifice and sudden expansion. Similarly, for part A, also two sets for PVC and two sets for galvanized. And again, the difference should more than 30%. Do you have any more question? No, actually, we already provide everything in UCS Canvas. Here you can see the formula that you need for part A, the calculation that you need. I'm not sure about the due date of the report. Let me check it. Oh, okay, thank you. Week 8. So again, try to submit it on time. Otherwise, you will lose 25%.
Once again, what's the deadline for the report?
Length?
The deadline for the report.
Should be week 8. So I will have a look in subject outline first.
And how much is it? Oh, week 8. Yeah, someone just messaged.
Oh, okay.
Yeah, and the weightage is 25%.
No, the wage for this lab report is 15%.
15%, and it's due in week 8, yeah?
Let me check it.
Yeah.
Yeah, 50% and with it.
Yeah.
Yes.
Yeah.
Okay.
Thanks.
Do you have any more questions?
No, that's it for today.
Yes. And if you need this slide, also I can give you if you want.